So we've been talking about various types of forces due to tsunamis that structures need to be designed to resist. So let's move on in that same vein, and we're going to talk about one more type of loading. And these loads are those that are actually caused by debris, which is floating with the wave. From lots of pictures from various past tsunamis, you can begin to get an idea of all the debris that gets picked up and carried by the wave as it comes on shore, from trees and logs and soil, boats, uh, just all kinds of wreckage from other structures are all moving in that wave, any of which may hit a structure as it comes on shore. So the wave can carry all of this debris with it. We need to consider that all of those things may be potential objects to strike our the building that we're trying to design. So the ASCE code has section 6-11, which actually goes through trying to quantify the amount of force that we need to consider. There are actually two methods provided in the code. There's this simplified method in section 611.1, and there's a much more detailed method which goes through multiple sections and allows for a much more detailed determination of potential forces. Now, one thing we want to keep in mind is that if we're in an area that the inundation is going to be less than 3 feet, then we're not going to need to worry about this. And if we are building something in risk category 3 or 4, hazardous or essential structures, especially if they're being built near a port or a harbor facility, there are going to be a lot more items to consider than the ones that I'm going through in this presentation. So let's start by looking at this alternative simplified method, which has a very basic formula that the impact force is going to be 330 times C sub O times I tsunami. This value comes out in kips, and it's going to be a single force that we need to consider being applied to our structure anywhere that creates the worst loading on the element that we're considering at the time. This value of C sub O is called the orientation coefficient. The code says we're going to use a value of 0.65. One thing to think about this is it's likely that this debris that's floating on the wave is going to strike our structure head on. It's probably going to give some kind of a glancing blow as it goes by. The value of ISU is the same one we use for the importance factor for based on the tsunami risk category for buildings that are either essential or hazardous. There is one important item in the code that says that F sub I can be reduced by 50% if the project is not located near a port or a harbor where large ships, barges, or shipping containers are located. So for the vast majority of the shoreline, we probably are not near this type of a shipping facility. So if we put those numbers together, one for I tsunami, 0.65 for CO, and we take that 50% reduction, we end up with a force of 107 kips. But we need to consider that it could be applied anywhere that will cause the worst situation to be in our structure. For a cantilevered system like this wall, the worst position would be to have it all the way at the top as high as it could go, which would be wherever the run-up elevation is. We do not need to consider the force being applied anywhere higher than that run-up of the water. But when we get to something like a frame, then we have to begin to think about some alternative locations. If I'm trying to determine the moment on the bottom of this frame, it may be that the worst position for this load is somewhere near mid-height of that column. Whereas if I'm trying to determine the shear, the worst shear on the column is probably when the force is located at the very bottom. So I may have to do two analyses depending upon whether I'm trying to determine the bending strength of the column or the shear strength that the column needs to be. So even though we're considering only one force at a time, we may need to consider multiple locations. And in fact, if I'm checking the shear at the top of the column, I may need to move that force all the way to as high as it possibly could be. The alternative is to use this more detailed method, which covers several different sections of the code. Each section is quite in depth itself. So this ends up with a rather long calculation to complete, but it does provide a more precise value and very likely a smaller value when we do more engineering work. So there's one section that talks about wood logs, another vehicles, another section just talks about boulders and concrete debris. There's one for shipping containers, and there's one for extraordinary debris, which covers a wide variety of miscellaneous items. You'll notice that there's a section missing, which is 5. 611.5 is actually the part of the code that tells us when we are close to a harbor and a port facility, and we need to consider the potential impact of those items. So in general, summary, we need to consider that this tsunami wave not only has more density, but it also is carrying debris. There's multiple types or sources of what that debris could be, everything from trees and wood poles, cars, all the way up to shipping containers and ships on its own self. The code allows us a simplified method, which is a short calculation to a single force. But as engineers, we need to consider there may be multiple locations that force needs to be applied, depending upon what I'm trying to determine the design characteristics for the structure. And similar to the hydrodynamic forces, the magnitude of that force needs to be increased based on the risk category. Thank you very much.